So we are going and moving on to the second problem in our kind of practice final exam. So again, this one, second question will cover basically lecture 9, so polymers. So the problems, we're looking at a new polymer material has been discovered, very interesting properties, but we can look at some of the monomer structures below. So we have 4 polymers, A, B, C, and D, to kind of choose from and work with. So let's go ahead and read what the problem is asking for. So first problem just says, describe how the end-to-end distance of the polymer chain, so this mean squared end-to-end distance, R squared, scales with N. N is essentially your number of monomers for a theta solvent, a good solvent, and a bad solvent. So let's kind of sketch out kind of how each of these looks. So theta solvent, good, and bad. So when we're working with a theta solvent, our polymer is just kind of relaxed. It's kind of wiggling, random coil. If we're in a good solvent, we want to maximize those monomer-solvent interactions, so it's larger. And a bad solvent, we're kind of highly coiled, right? So we could also, let's go ahead for a theta solvent. Let's describe, so my energy of the monomer interactions and the energy of the monomer-solvent interaction. So for a theta solvent, these are kind of basically like equal, right? They don't, there's basically the monomer, the solvent, monomer-solvent interaction. Neither of those dominate. So that's why you're kind of in this theta solvent in the melt. You'll kind of hear that kind of a lot. So your energetic interactions, they kind of cancel each other out. There's no kind of, you're at this kind of equilibrium of excluded volume. But again, a little bit beyond the scope of this class. Now, for a good solvent, we know that our monomers and solvent like each other. So we know that this interaction is going to be, in terms of energy, very, very large and very, very negative. So basically, so magnitude is large and negative. Here, monomer-solvent interactions, they're going to be large, or, again, large, or but basically positive. So remember, we always want delta G to be less than 0. So for a good solvent, these interactions dominate. They are large and negative. Monomer, they don't like each other. They want to move away from each other. So that interaction is positive. For a bad solvent, it's the opposite, right? Our monomer solvent, the polymer does not like the solvent that it's in. So this interaction would be large and positive. And this one, the monomer, they like each other. That's why the polymer collapses in on a coil, and that is going to be large and negative. So how would we expect, again, we kind of see schematically here. The good polymer is going to have the largest scaling, the largest R squared end distance. The bad will be the smallest, and the theta will be kind of in between. So for a theta solvent, your mean squared end distance right there is going to be, let me scroll right here. So that is going to scale as N. And this is in the notes. And for this year's class, we really didn't kind of due to the remote teaching aspect and kind of transition, we didn't really talk too much about the scaling with N. So that's probably not going to be a question that you're going to kind of see pop up on your exam necessarily. The good solvent scales as N to the 6/5, and the bad solvent N to the 2/3. So you can see our intuition is correct, right? This is larger than our theta solvent. This is smaller than our theta solvent because we're collapsed, and we're in the middle right there. So that's it. So let's look, and actually, we've already answered C as well. For a polymer and a good solvent, which interactions are more favorable? Monomer or monomer solvent, so that is the monomer solvent. Which is more negative? Monomer solvent. How about for bad solvent? Switched, vice versa. So, but let's answer B. How does the number of configurational entropic states, so what we're talking about here is delta S entropic, which scales with this, which is the number of microstates. So how does the number of microstates, or the number of configurations, or your configurational entropy, how does it change when it's stretched? How does it change when it's compressed? So if I have a polymer here that's kind of relaxed, if you close your eyes, I could draw this polymer a lot of different ways. And it would still, basically, I can rearrange this polymer in multiple ways. But if I stretch this polymer out like this, take it to the extreme of just pulling it all the way to its end-to-end distance, what's going to happen to the number of ways I could kind of rearrange that polymer? My Here, for this problem, let's call this A. My gamma A here, the number of microstates versus, let's call this my B state. So gamma B. And then let's take a look at when it's very compressed or highly collapsed. We'll call this state C. Gamma C. What is going to be the relationship between the number of microstates of A and the number of microstates of B? Which is going to be larger? Well, the number of microstates of A is going to be larger because, again, I could rearrange these much more kind of simple or straightforward. There's a larger number of ways I could reconfigure my state A as opposed to B because, again, I'm restricting the number of microstates by pulling it out and stretching it. The same thing can be said for C as well. When you're highly compressing it, you're reducing the number of available microstates, and that's we have the same relationship right here. Excellent. Now, I'm going to erase quite a bit here. So let me get my eraser, and let's get to erasing because I love question D. So question D is asking us, rank the glass transition temperatures of the 4 polymers above. So let's take a peek. What's happening here? So let me erase. Sorry, that's taking some time there. Erased. Let me just erase these guys so that we can work and make another table. So remember, the TG depends a lot on the chemical structure of a material. Specifically, we kind of identified one, we want to look for interactions. So interactions between the monomers or between the side chains. If we have interactions, strong interactions, for example, H bonds, polar, ionic, those are going to increase our TG. Because TG, remember, is the transition from the glassy state where the polymer is almost frozen to the rubbery state or almost liquid-like state where the polymer can kind of wiggle and move around. So if there's interactions between the chains or even intramolecular interactions between the in your monomer unit, that is going to kind of make it more difficult for the polymer to kind of move and wiggle around. So the same that is one thing that we're looking for here. The other thing is the ease of rotation on the backbone. Ease rotation. And it could be along the backbone or the side chains here. So if we have like lots of double bonds, if it's hard to kind of rotate, that is also going to increase our TG. So these are the two kind of main ones that we deal with. Also, you can kind of think about the excluded volume. So how much excluded volume is there? If there's a lot, or excuse me, not excluded volume, free volume available. So if there's more free volume, again, the polymer is able to kind of wiggle around. But again, we're going to focus more on these two right here. So let's look at A. Do we have any interactions in A? Not really. I mean, you could have maybe some, van der Waals interactions between these, but they're pretty weak. So there's no interactions. What about the ease of rotation? Well, these are just single bonds. These are kind of small pendant chains. So these are going to be pretty easy to kind of rotate around the chain here. So that's not going to be an issue right now for this kind of polymer. So at the outset, I'd say that this TG is going to be my TG of A is going to be pretty small. So I'm going to put it like right at the end there. So let's look at B. B, are there any interactions going on? Well, you could see here this fluorine group. That is very electronegative. So there could be some polar interactions that could be occurring here. Also, there could be some repulsion too between the other chain as well. So that there might be some interactions there. There actually will be due to that fluorine group. That high electronegativity wants to grab all the electrons from carbons and H, anything kind of near it. So that's going to be kind of an issue that we're going to have to deal with. So if we have those polar interactions, the TG is going to be larger. So I would maybe rank this one the next. So my TG of B is greater than A. Now, we can also kind of think about and look at ease of rotation. This one's fairly easy to rotate around because, again, small pendant groups, even though you have the repulsion from the F and a larger kind of pendant group there, it's still going to be relatively straightforward. Now let's look at C. Do we have interactions? Yes, amide linkage, H bonds, all the way across here. So check that one off. What about ease of rotation? These rings, these aromatic rings, they have lots of carbon double bonds in here. It's extremely difficult to rotate around here. So I'm going to put my TG of C at the very end here. Because again, we have both interactions, ease of rotation, very difficult when you have any of these kind of aromatic rings. They're all carbon-carbon, they're just double bonds all around this material. And then finally, we're left with this polymer, polymethyl methacrylate, actually. But anyways, so what's going on here? So do we have any interactions? Well, possibly due to some of these, you might have some polar interactions going on here, but they're not, super, again, O's and oxygens, not too bad. But what about the ease of rotation? If this molecule wants to kind of rotate around here, that's going to be extremely difficult. So that's why I would put my TG of D greater than my TG of B. But again, these two, I can kind of see an argument to be made either way and to flip. But this one and this one, I'd say those are fixed. So those would be my rankings of TG. And again, you have to justify based on interactions, ease of rotation primarily. Excellent. Now, finally, looking at the DSC curve below, which curve corresponds to an amorphous? Which one corresponds to a semi-crystalline polymer? Label the TG for each curve. What can you deduce about the structure of the polymer based on the TG value? Label endo and exo. So way back, or not way back, but back to our DSC analysis. So we need to figure out which one is amorphous. Amorphous, semi-crystalline. So, and we need to label the TG. So let's start with first, we see kind of this peak here. So whenever we see kind of this peak, or actually we can even start further. So we know that to identify the TGs, TG is a second order phase transition. So when we plot heat flow, basically this delta H versus T, we are not going to expect to see a discontinuity. So when we see melting, which is associated with semi-crystalline, that is a first order transition. You'll see a discontinuity, a spike, or a peak here. So as we increase temperature, we see this kind of peak here. And if we have, if that peak is going up, and you can see here, the TG is a second order phase transition. So we will see a change in slope. So we could see a change in slope here and a change in slope here. So here are our two TGs for the two different curves. You kind of pick the midpoint there. So let's think about heat flow. If at low temperatures, we know we're glassy. So as we increase temperature here, we're getting enough thermal energy where we can kind of break those intramolecular interactions in our polymer chain and start to wiggle around and move. So if we need to absorb energy to make this happen. So therefore, absorbing energy, we know that's endo. So if we're heat flow, if we're absorbing it, endo is up, exo is down, and we're ready to go. That's it. So endo, exo, we've got our TG. Now, which one of these is amorphous, which is a semi-crystalline? Well, we know amorphous polymers will not have any crystalline region. So they will only exhibit a TG. So in this curve, the blue curve doesn't exhibit any first order phase transition. So this is our amorphous polymer. Now this curve here, once we labeled endo and exo, because again, this could have been a, we didn't know necessarily at the outset that this could be a recrystallization curve, but this is our TM. This is our enthalpy of melting, enthalpy of fusion. We've seen that before in our DSC lab. But we know this material has a TG and a TM, so we know that is semi-crystalline. And we know that this semi-crystalline polymer, the TG here, is lower than the TG of the amorphous polymer. So the amorphous polymer might be more rigid. It might be harder to rotate. It might have some interactions, more interactions along the chain compared to the red curve. So yeah, that's about it for that question. So for polymers. So that's the kind of the basics that you'll be asked. So next time, let's see if I can get to the next page. Next time we're going to go all the way back to lecture 1, and we're going to try to figure out what are these directions, what are these planes, and all of our kind of good old questions. So yeah, see you in the next video. Thanks. Have a good one. Bye.